Hello, college algebra student. We were working on the last exponential growth example, but I didn't manage to finish it before the 15 minutes. So let me just finish it. So we say this is an example about compound interest with a rate of 0.055. So you can write the exponential model very clearly, and then they ask us how long does it take for it to double. So that would be ln2 divided by k. In this case is ln2 divided by 0.055 because that is the given growth rate. So it's just a matter of putting into the calculator. So we use decimal calculator. I think because I show you how to do it on the calculator, so it takes longer to finish the whole thing. So it's ln2 and then divided by 0.055. So the time is 12.6 years. So if you have a rate of 5.5% continuous growth, that's about 12.6 years to double. How long does it take for it to grow to 8,000? So that means y is 8,000. T is unknown, right? So this is the V. So you use the model, but you are not plugging in T, you're plugging in Y. And then this is 3,200. E to the 0.055. T is the unknown. So to solve for T, you just do the standard thing, divided by the cleanup outside, right? So cancel the 2 0. So 82 over 30, no, 80 over 32 equal to E 0.055 T. To solve for T, you add ln on both sides. So ln 80 over 32 is equal to ln E 0.055 T. And because 0.055 T is an exponent, you can move it out. So ln 80 over 32 is equal to 0.055 T only because ln E is actually 1. So T would clearly be just this ln. You see that you're almost doing the same thing again and again. Divided by 0.055. So it's just a matter of putting in the calculator. Let's do clean it up. ln 80 over 32, and then close it, divided by 0.055. 16.7 year. So earlier we say 16.7 T equal to 16.7 year. Oh, 16. So earlier after 18 years, it become 8,600. So it'll be a little less than 18 years. So that makes sense. 16.7 years. The next part, the last part of chapter 6.7 is exponential decay model. So exponential decay is similar to exponential growth. We can still write it as a0 e to the kt, but in this case, the k is negative. So the decay rate is actually negative k because this is already a negative number. So you would have the absolute value of this k itself would be the decay rate, and then a0 is the initial amount. Right? So because it's decaying, so it would be getting less and less. So another way to look at decay would be the time for it to decay to half, and we call it half-life. So sometimes we would use half-life to model it. So let's say half of a0 would equal to a0 e of kt, and we want to find out what this half-life is. This is the half-life time that would have half of a0. So divided by a0 on both sides. So our equation become 1/2 equal e of kt. So you can do ln on both sides. ln 1/2 would equal to e of kt. Right? So what would oh no, this is ln. So k would be outside, so it would be kt equal to ln 1/2. So t is equal to ln 1/2 over k. Because k is negative, so this would work. So and the book used so there's another formula for it, is when we do ln 1/2, we can also think of it as ln 1 minus ln 2, right? Over k, that is equal to t. That's the half-life time. We actually call it capital T. But ln 1 is 0, so it becomes this one. So you can use, some book do use ln 1/2 over k, some book use negative ln 2 over k. So both are half-life. So if you know your k, you can find half-life. If you know half-life, you can also find k. And once you know half-life, you can also, just like when you have doubling time, you can use this model to represent the exponential growth, A0 1/2 t over t. But in this particular case, t is half-life. Okay. So how do I solve problem? So to solve problem, you want as much as possible to write either one of them. If you know your decay rate, then you use this formula, E of kt. If you know your half-life, then you use this formula. And then anytime you want to find, if you don't have any of them, you would need some time. You would, that show you y and that's t, so you can solve for a0 or k. To find doubling time is negative ln 2 over k or ln 1/2 over k, right? So these are the approach to solve a problem. So let's look at the first example. The first example say there is a medication of 80 milligram decay continuously in a patient's body at a rate of 40% per hour. So, we know it is decay and it's continuous rate. So this is k. K is 0.4 if you change it into decimal. So the model would be, we'll adopt the initial is 80, E model, okay, the base E model, 0.4 T. Okay. So what is the, it's not negative 0.4 because it's decay, so it is subtracting, right? So it's negative 0.4. So don't do it 0.4, 0.4 will be growing. So this is not, this is decay. How much will be in the patient's body after 5 hours? So it's just plug in, right? So you know the time is 5. So it'll be E of negative 0.4 times 5. So if you put it in a decimal calculator or scientific calculator, it's 10.8 milligram. What is half-life? Half-life is related to ln 1/2 over k, right? Which is negative 0.04 or negative ln 2. You can see that both are the same, negative 0.04. Put in the calculator, so this is 1.7 hours. So that means in 1.7 hour, it's going to cut into half. So they say every hour is cut 40%. So if you want to, you want to cut 50%, that makes sense. It's 1.7 hours, little more than 1 hours. Okay, example 2. If you have 560 milligram of radioactive compound and it decayed to 400 after 80 minutes, so this is A0, that's lucky. But we don't know K, we just know that it decayed to 400, so this is Y value, and this is T. So we have to solve the exponential model. So we just write it first. We would say our model is Y equal to A0, E of, A0 is 560, E to the KT, right? So we don't know K, so we have to solve for K. So 400 is equal to 560 E of K times 80, right? 80. So here this tells us Y is this one, 80. So the only unknown is K, so we want to solve for it. So divided by 560, 400 over 560, don't think I have enough space here. Equal to 80k, e to the 80k. Add ln on both sides. Ln of 400 over 560 equal to ln of e to the 80k. Of course, the 80k is going to go outside as a coefficient. So I would end up having this ln of 400 over 560 equal to just 80k times ln e, which is 1, right? So we don't have to write it. So k would equal to ln, this is very big, 400 over 560 divided by 80. So put in the calculator, I got k is equal to negative, we have to do a more decimal point, negative 0.004259. Okay, so that is k. So what's the half-life? Half-life is ln 1/2 over negative 0.004259. If I do that, that would equal to 164.8 minutes. So I can just do one for you to see is ln 400 over 560, right? Just so that you know how to do it. Divided by 80. So see 0.004259. So do as much as possible. And then the other one was ln 1/2 divided by k, which is negative 0. The one that we just see 0.004259. So you can 164.8 minutes. That's how we do. The third example is lucky one. We have half-life. So the exponential model is really easy. It's why? Because we would use half as our b would equal to do we know what we begin with? Oh, we begin with 800 milligram. They talk about in part B. Okay, so 800 1/2 to the t over 241. So this is not multiplying, but this is in the exponent. So this is the exponential model. How long does it take for 90% of this to remain? What is 90% of 800? 90 times 0.9 is 720, right? 720 milligram equal to how long? That means time is, don't know, equal to 800 1/2 t divided by, no, 4, this is not 241, it's 482. This is the half-life. This is the name of the compound. 482 is equal to t. So 482. Right? So if I solve this, I divide it by 800. And this would actually be 2.9 equal to 1/2 to the power t over 242. To solve the unknown here, we do ln 0.9 equal to ln 1/2 of t over 282. So move the t over 282 on the front, and then I would have ln, not enough space, ln 0.9. I might not be able to finish this over ln 0.5. 1/2 is 0.5 equal to t over 280. No, 482. 482. I keep writing the wrong number. 482. So t would be equal to 482. You multiply 482 on both sides, and then ln 0.9 over ln 0.5. Put in the calculator. Earlier I did 73.3 year. Okay, so that is how you do it.